Thin film functionalization of carbon nanotubes by loading AU nanocluster for flexibility gas sensor devices. In this presentation, we'll see some introduction regarding this topic. Later, we'll see the structure of carbon nanotubes, types of carbon nanotubes, the sensor design, and we'll discuss some of the results for the experiment that has done with the sensor, and finally the conclusion. Gas sensors are employed in various applications, including medicine and environmental monitoring. Flexible portable electronic devices are a potential alternative to more expensive devices based on silicon technology. This presentation proposes a flexible CNT based gas sensor on a low cost polyimide substrate that responds immediately to carbon dioxide, isopropyl alcohol, and NH3, that is ammonia, at room temperature. Highly uniform CNT thin films are prepared using a reliable and reproducible transfer process are used as resistive networks. Carbon dioxide is one of the most abundant source of carbon source. Gas emissions from industries and refineries, power plants, and automobiles are observed reasons for increased CO2 in atmosphere. This growing rate of CO2 is from anthropogenic as well as natural carbon sources. Ammonia is a hazardous and caustic gas with a characteristic pungent odor. Ammonia is biosynthesized from normal metabolism of amino acid, which is toxic in high concentrations. Isopropyl alcohol is a chemical compound that has a concentrated odor which is colorless. Vapors of isopropyl alcohol is denser when compared to air and it is highly combustible with very wide combustible range. When it is mixed with air or other oxidizers, it can explode through deflagration. In the researches that are happening in recent years in sensor field, importance is given to materials that is used for sensing. Sensing layer has essential role in sensors implementation. Chemical sensors are most preferred in new generation researchers because of their low cost, high precision, low power and portable characteristics. They also possess high gas adsorption capacity, captivating physiochemical and electrical properties. Carbon nanotube CNT is the most promising nanomaterials because of their large effective surface area with many available sites for gas adsorption. The structure of carbon nanotube. This includes like carbon nanotubes are allotropes of carbon with a nanostructure. When a graphite sheet are rolled into cylindrical shape, their edges are joined to form CNTs. The chemical bonding of CNTs is entirely sp2 hybrid carbon atoms. These bonds are similar to graphite and stronger than bonds that are in diamond and alkanes. These are highly sensitive because of its cylindrical shape and it is also has high aspect ratio. Now we'll see about the types of nanotube structures. There are two types of nanotube structures, namely single wall nanotubes and multi-wall nanotubes. Single wall nanotubes are the one-dimensional cylindrical shaped allotropes of carbon that have high surface area and aspect ratio. Because of their small diameter and large aspect ratio, single wall nanotubes are considered one-dimensional material. Multi-wall carbon nanotubes are also allotropes of carbon. Their walls are formed by multiple one-atom thick sheets of carbon. Multi-wall carbon nanotube consisting of multiple rolled layers of concentric nanotube of graphene inside their nanotubes. Now we'll see the sensor design. The figure 1 schematically shows a procedure for fabricating a flexible gas sensor based on CNT thin films obtained using chemical vapor deposition. The substrate was thermally oxidized to form a silicon dioxide as in SiO2 layer that has a thickness of approximately 200 nanometer. This is shown in figure 1a that acts as a catalyst diffusion barrier. A 10 nanometer thick iron layer was deposited via splattering. Then silicon substrate were loaded into aluminum oxide board. This was placed horizontally to the tube furnace. Gaseous nitrogen was then introduced into the reaction tube at the flow rate of 100 sccm and a pressure of 6.5 torr for 20 minutes. This pre-treatment was performed at 600 degrees Celsius. When the temperature reached 700 degrees Celsius, the flow of nitrogen was stopped and the flow of acetylene, as in C2H2 reactant, was switched on at the rate of 30 sccm at 3.5 torr for 10 minutes. After the flow of acetylene reactant was terminated, the reactor was slowly cooled at room temperature in nitrogen ambient. In the transfer process, CNTs were first grown on SiO2 substrate, then acrylic adhesive was coated on the flexible PI substrate. This transfer process can be completed quickly and it is shown from the figure 1D to 1G at room temperature. An electron beam was utilized to evaporate a control load of noble metal like Au nanoparticle all over the CNTs to an equivalent nominal thickness of 5 nanometer. By this method, Au will be adsorbed on the surfaces of CNTs. To fabricate a CNT gas sensor, a 100 nanometer thick silver contact was evaporated using an electron beam system onto the CNTs to form contact electrodes. A metal mask with a metal contact of width 1 millimeter and length 5 millimeter and a detection area of 25 millimeter square was used. Gas sensing experiments were performed at high vacuum current voltage measurement system. In figure 2a, it can be seen that a digital photograph of an Au nanoparticle decorated CNT network on a flexible substrate. Some of the Au nanoparticles that are coated on the CNT sidewalls were isolated while some joined together, increasing their size close to 5 nanometers. Figure 2b shows the top view of field emission scanning electron microscope, that is FESEM, images of specimen under extreme bending. Owing to the adhesion between CNTs and flexible substrate, the pattern was maintained even when the substrate was extremely bent. Figure 2c is the XPS spectrum of the AU coated CNT, includes the AU 4F 3 by 2 and AU 4F 5 by 2 doublet with bending energies which is approximately equal to 86 and 90 electron volts respectively. Such a doublet is typical of all AU peaks. Now we'll discuss the results of the experiment that has been conducted. Figure 3 shows the IV characteristics of CNTs before and after AU deposition. Based on the measurements, the resistance of pure CNTs is roughly 285 ohms, indicating typically good CNT conductivity. The resistance of AU CNTs was only 241 ohms. The microscopic image shows that AU nanocluster did not form interconnecting conducting pathways between AU CNTs, so the decrease in resistance must have resulted from net charge transfer between the AU nanoclusters and the AU CNTs. It is well known that addition of small amounts of noble metals such as Au to the elements can promote not only gas sensitivity but also the rate of response. Larger sensitivities observed for multi-walled carbon nanotubes with AU should be attributed to the enhanced interaction of multi-walled surfaces. The insert in figure 3, which is the pure CNTs surrounded by air, shows that oxygen molecules adsorb on the multi-walled CNT surfaces to generate chemisorbed oxygen species by capturing electrons from the conductance band. The transient responses to volatile organic compounds are shown in figure 4 as obtained from continuous gas monitoring with filling pressures ranging from 50 to 800 millitorr. The measurements were made by injecting various amounts of gas into a chamber that contained the CNTs and then increasing the pressure by pumping at a fixed voltage of 5 volts. Figure 4a shows the plots of AUCNT sensor versus AUCNT sensor response versus CO2 gas pressure at CO2 concentrations of 50, 100, 200, 400, and 800 ppm. The measured sensitivities were approximately 1.5%, 2.3%, 3.1%, 4.1%, and 4.8% respectively. Figure 4b shows the plot of AUCNT sensor response versus ammonia gas pressure at ammonium gas concentrations of 50, 100, 200, 400, and 800 ppm. The measured sensitivities were approximately 1.7%, 2.5%, 3.4%, 4.4%, and 5.2% respectively. Now, figure 4c shows the plots of AUCNT sensor responses versus isopropyl alcohol gas pressures. The response of unmodified CNT sensors is lower than that of metal modified CNT sensors for all vapors examined due to the enhanced catalyst effect. This means that the metallic nanoclusters did not impart any degree of selectivity but only enhanced sensitivity because of the different absorption energies that exist between different molecules and the CNTs. Figure 5 plots the sensitivities of the sensors with and without AU nanoparticles to different vapors at a concentration of 800 ppm based on figure 4. All sensors coated with AU nanoparticles exhibited higher sensitivity than that of uncoated sensors. The sensing mechanism for the AU-CNT sensor arises from interaction between the reducing gas and AU nanoparticles and CNTs. CNTs contain 5 potential types of adsorption sites, namely external surfaces that are coated with metal nanoparticles, internal sites, interstitial channels, external groove sites, and external surfaces not covered with AU. To study the reliability of the flexible CNT sensors, the sensors were exposed to 3 cycles of 50 ppm carbon dioxide vapors. The responses are plotted in figure 6. The radius of curvature is 1 cm. The strength of the sensor response remained unchanged after repeated cycle of exposure and recovery. Notably, the sensor response was good in the tested bending state. These results reveal the potential of the developed flexible sensor to be reliably operated even in passive recovery mode with an acceptable loss of sensitivity, making them suitable for low cost and low energy applications. To conclude this presentation, we can see that a simple method was applied for the direct transfer of high density CNTs from SiO2 or Si substrate to a flexible substrate for carbon dioxide, ammonia, and isopropyl alcohol gas sensing at room temperature. The surface modification of CNT's networked films with size controlled AU nanoclusters enhanced gas sensitivity. The flexible gas sensor exhibited high sensitivities of 4.8%, 5.4%, and 5.2% at room temperature for ambient carbon dioxide, ammonia, and isopropyl alcohol gas concentration of 800 ppm respectively. The speed and stability of the sensor of the fabricated sensor were both favorable. The results clearly demonstrate the feasibility of manufacturing flexible CNT gas sensor using the transfer process. These are the few references that are used in this paper. And yeah, thank you.